Hello and welcome to this introductory course, Developing Real-Time Applications with WebRTC by Packet Publishing. Allow me to introduce myself. I'm Atul Pundir. I have been a full-stack developer for about 8 years now. Being a full-stack developer, I got great opportunities to work on cutting-edge technologies on front-end, back-end, and database sites. I have been involved in developing projects in WebRTC since 2012. Coming to my academics, I have done my Master's in Computer Management. WebRTC is increasingly becoming popular, and more people are talking about it. There are other guides on the web that introduces different parts of this project. However, they tend to focus on just a few layers on a specific problem. Our goal will be to teach you WebRTC both conceptually and practically. Not only how to program it, but also learning to identify which kind of problems could be related and solved by using WebRTC, a free and powerful technology. The goal of this course is to develop an end-to-end WebRTC application while understanding every bit of the technology. We will start from point zero and cover the basics and create an end-to-end WebRTC application. Hence, this course has been divided into 5 sections. In section 1, we will be covering Introduction of WebRTC, what WebRTC is, and how it differs from existing technologies like Flash or plugin-based solutions. We will also be setting out programming environment. In section 2, we will be covering JavaScript API for WebRTC. We will be looking in detail about GetUserMedia API, peer connection methods, and SDP protocol, which are the backbone of WebRTC. In section 3, we will discuss the different options we have for signaling to establish WebRTC sessions. We will also discuss why there is no mandatory signaling protocol. We will implement our own very simple signaling server in Node.js to establish the calls. This way, we can use JavaScript for both the client and the server side. All the elements coded in the previous versions will be glued to create a functional WebRTC application. Section 4 will give our application a nice shape, as we will be initiating a WebRTC session, receive WebRTC session, and establish our first session and pass out the audio and video streams. Once we are done with the application, in Section 5, we will be exploring the developer's tools, which will help you improve and debug your application. The end goal of the course is to make you understand how WebRTC works by developing a WebRTC application. Only prerequisite for this course is to know HTML and JavaScript. So, let's begin this journey together and start learning. I'll see you in the next video. Hello! In the last video, we went through the topics which we will cover in this course. In this section, we will try to understand what WebRTC is, how it differs from other technologies like Flash, Java, or other plugin-based applications. We will also be setting up our developing environment. In this video, we will take a further look at the main motivations and characteristics of WebRTC, what WebRTC can do, how it does, and some different research domains where it can be used are some of the questions whose answers we want to introduce here. As per Wikipedia, WebRTC is an API definition drafted by the World Wide Web Consortium that supports browser-to-browser applications for voice calling, video chat, and P2P file sharing without the need of either internal or external plugins. WebRTC is a recent technology dating from 2011, offered by some of the most popular web browsers nowadays. It permits us to be able to share real-time media and data from a browser in a native, secure and reliable way. The special thing about WebRTC, which is something we'll see during this course, is that it handles all those elements without needing to install any plugins, since the functionality is fully implemented in a native way from the browser. Instead of them, we currently have at our disposal a new and really powerful API. We'll be able to establish P2P between computers over the web, with lots of possibilities. WebRTC uses some capabilities from HTML5 in order to manage the way we display or interact with our multimedia streams. And there is also a JavaScript API, whose methods will allow us to create connections with other peers. managing all the steps to transmit the media and to play with it. There are general domains where WebRTC could fit pretty well. For example, telemedicine, healthcare and emergency at distance, call centres, agent calling, click-to-call, business telephony, etc. E-learning, real-time office hours, real-time online lectures. How is this possible? Well, practically all that you could imagine doing with your camera, microphone, or even your screen is feasible using WebRTC. There are some popular and concrete ways in which this technology is used for those purposes. Calling and multi-conference apps for 2 or more people, for video conferencing or conventional audio calling. Even we'll be able to reach the public telephone network if we properly manage the way we connect to it. This means browser-to-phone calling, not just browser-to-browser. Audio and video processing. Since we have a pretty good control over video and audio streams, recording, processing, etc., this would lead to some applications as HCI, human-computer interaction, making people able to control their computer with their eyes or gestures through a camera. Remember that video can be recorded and processed. Audio applications. There are a lot of possibilities for this kind of purposes. Some examples to see: https://www.webrtc-experiment.com. Data channels, P2P connections, for sending real-time traffic with low jitter, a phenomenon affecting badly to our traffic. Not only media traffic, but also pure data. We have AJAX, WebSocket, server-side events. Then what is the need of another communication channel? We need it because all 3 technologies are designed for communicating with a server. However, RTC Peer Connection API takes a different approach, which is used to establish peer-to-peer connection. In the next video, we'll see how WebRTC is different from other technologies like Flash, Java, or other desktop applications. Hello again. Some years ago, web apps were totally different from desktop apps and mobile apps. But now, thanks to all the functionality given by HTML5, it is possible to build pretty nice web applications, which are on par with desktop and mobile ones. Each day, there are more and more at the same level, attending to what they can offer users. Besides, plugins are no longer necessary. We just have to install a browser. In the previous video, we understood what WebRTC is and where HTML and JavaScript fits, as well as looked at domains where WebRTC is being used. Before we dive into the code, it's important to understand how WebRTC is different from other technologies like Flash, Java, or desktop applications. Let's check that in this video. JavaScript was very restrictive, and it didn't allow media access. Now, it's possible to easily reach camera, microphone, and even screen if the user wants to. This is how we're able to build multi-conference applications using a browser and WebRTC. Let's compare it briefly to existing technologies, trying to keep fairness. We are just interested in showing you what's interesting about WebRTC. During the year 2000, Flash has been very popular on the web, but this plugin from Macromedia is working over TCP, a protocol not quite well prepared for real-time communication. Concretely, voice-over IP developers have found that using Flash would bring an unacceptable latency to conference applications. WebRTC currently supports both TCP and UDP protocols for transmitting the information. UDP is quite convenient for real-time media communication, as you can see in some applications as Skype and similar. UDP isn't better than TCP, they are just for different purposes. TCP looks for high reliability data transmissions, and UDP for low overhead transmissions, speed instead of reliability, just that. New Flash products have used successfully UDP protocols, but having to use intermediary servers. Java is simple, well-known and distributed, but it doesn't seem to be as equipped to handle multimedia as WebRTC or Flash. There is a big lack of digital signal processing (DSP) capabilities for VoIP, as echo cancellation, gain control, and some fighting noise techniques. There are some libraries for that, that's true, but they are not so easy to implement, and they depend on the operative system you're using. A desktop application will depend on the OS too, on their libraries, and maybe other software dependencies as well. That won't happen for WebRTC, which is supported in popular browsers available for a lot of operating systems, including mobile ones. To summarize, we are not saying that WebRTC is better than other technologies, but just that it was designed for solving VoIP and DSP issues specifically, while other solutions might not be so oriented to solve this kind of problems. Besides, we cannot forget that WebRTC is supported by giant companies like Google, Mozilla, Microsoft, Ericsson, which have already invested a huge amount of resources on it. New features are constantly being added as we know. It is continually evolving. In the next video, we'll be setting up our programming environment to kickstart our WebRTC application. Hello. In the last video, we understood how WebRTC is different from the other technologies. This is the last video of this introductory section. Finally, we are going to take a quick look over the main tools that we will use for developing our nice WebRTC applications. In this video, we will choose compatible web browser and a source code editor catering to our needs. We will also touch upon the basics of signaling in WebRTC. We are just introducing the very basic software we'll be using during the next set of videos for building applications in a pretty short period of time. We need an editor for the code, where we will use methods provided by the WebRTC API, a WebRTC compatible browser, where we will choose Chrome for its developer tools. We'll briefly mention that we might need a server. And finally, we'll conclude that the coding part is incomplete. Something is missing. But keep calm, we will see it in section number 3. WebRTC provides a JavaScript API. This isn't strange at all. A lot of browser apps are based on JavaScript. Hopefully you are familiar with it. But even if not, it shouldn't be a problem. There are dozens of code editors suitable for writing our apps. Since JavaScript doesn't need to be compiled, you can choose the one you feel most comfortable with. Free software editors such as Vim, Emacs, Eclipse, or the not-so-free ones, Sublime Text. There are loads, and any of them would be fine. For instance, I have here installed a Sublime Text demo version. I like its colors and some features you can install on it. There are also some languages that compile to JavaScript, making programming easier. Examples of this are CoffeeScript or Dart. Nowadays, almost every popular browser is on its way to implement WebRTC functionalities. Is WebRTC ready yet.com contains an updated table about which WebRTC functionalities are already implemented. It's a good point to start choosing one according to your needs. Let's choose Google Chrome. Chrome, Firefox as well, offers us a developer console with a lot of tools that will make our life easier while debugging our apps. Knowing what's wrong or what's really happening. Not just logs, warnings or errors, but also the ability for watching events, CPU usage and performance, and a big etc. Servers are not a must for testing the main WebRTC functionalities, but keep in mind that even with WebRTC supporting P2P connections, our scenario could also work as a client-to-server one, when different people want to connect to each other and a server provides communication between them. So in this section, we have learned what WebRTC is, different components of WebRTC, and how it differs from other technologies. We also set up our developing environment. Besides, we'll see that in case we have to be careful. WebRTC won't provide signaling by itself. What does signaling mean? Imagine that Alice wants to call Bob. Where is Bob? What's his phone number or other identifiers for finding him? The issue is out of scope for WebRTC, and that's why a signaling protocol is required. This will be covered in detail in section 3. As we have set the foundation, now let's take a deeper dive into WebRTC's ocean in the next section. See you in the next section. Hello, and welcome to the first video of section 2. We have understood what WebRTC is and we are ready without development environment. This section will teach you the very basic elements you need to know to build your WebRTC application. We will learn how to use the getUserMedia API, peer connection method, and session description protocol. In this video, we are going to talk about the main JavaScript elements for providing WebRTC services, from capturing your local media to sharing it with whomever you want, just by using a few JavaScript functions. As we have already said, WebRTC provides a JavaScript API, an abstraction layer for reaching media and connecting to other peers in order to send data and media streams. So the first main function we'll take a look into would be obtaining the media streams from your camera, microphone, and screen. These streams can be accessed using getUserMedia. This is the first method that we'll study. Another important element of this API is the class RTC peer connection, which supports the connection between the different peers involved in the WebRTC session. It is used to handle efficient streaming of data between two peers. We already have our local streams and a connection. The next step will be to share them with another user, one or more people. But there's a problem to deal with before we dive into it. Since browsers have different capabilities, a negotiation is needed between all the implied peers to properly establish the sharing parameters of their streams. This will be done through SDP, or Session Description Protocol. It describes the media streams in a text format. We'll be studying it in detail in the video 4 of this section. The peer starting the communication has to obtain his media SDP and send it to the other peers. Using the method createOffer, once a peer receives this SDP, he would have to call the method createAnswer. You may have noticed that we spoke about sending the SDP, but WebRTC doesn't define how to do it. It's out from its scope. This is one of the reasons for which signaling is needed. The process will be explained in detail in section 3, but let's briefly introduce it. This process of signaling is called ICE exchange, where ICE stands for Interactive Connectivity Establishment. In it, the peers use different types of servers as relays. Because as an internet client, your IP address is private, for instance. Those servers help you translate your IP and your peers too. In this video, we've covered how the user can reach his local video and audio, which object represents the connection between peers, the methods for negotiating some parameters before calling, and finally, we've anticipated the ICE problem, related to how peers can find each other. In the next video, we'll go deeper in how to use the getUserMedia method, making it work on an easy example. Stay tuned. Welcome back. In the last video, we enumerated the different tools provided by the WebRTC API to make possible a connection, usually a video conference, between two or more people. In this video, we'll learn how to use the getUserMedia API by checking out an example of the method call on Chrome, writing an HTML document with JavaScript for writing the method. Before we dive in further, let's discuss the initial challenge faced by the WebRTC developer, the browser compatibility. Previous versions of the current browsers implemented WebRTC, but did not follow the standard notation. They used a different prefix, for instance, in Chrome and Firefox. Even when the new versions start using the proper notation, you cannot prevent users from having an updated browser. Most of them don't have updated browsers, but we would like to avoid this silly error at the beginning. Do you know what is adapter.js for? Well, it's a short and simple piece of code that just checks if your browser has WebRTC basic capabilities, as getUserMedia is, and if so, it uses the standard calling of the function, the proper one, depending on the browser, so it's an abstract layer. I already have adapter.js installed on my laptop, but if you want to install, you can go to github.com/webrtc/adapter. The code basically asks the browser whether it has some methods or not. For instance, if the browser presents Moz getUserMedia, we're sure it's Mozilla Firefox, and we can call the different non-standard notation functions. If the browser is Chrome, the prefix would be WebKit, and it's the same case. As you can see, the code is short and simple, with a couple of statements with instructions inside for attaching the media streams. So, we have a variable declaration for getUserMedia, reattached media stream, RTC peer connection. We have a debugging function called trace, which basically accepts string. Now check this out. We have an if condition, which is checking for moz getUserMedia. So if the browser is Firefox, this code will get executed. If not, it will check if it's WebKit getUserMedia. If it is Chrome, the code inside these brackets will get executed. So as a developer, you need not worry about which browser the user is using if adapted.js is used. Finally, here we are. I have created two files. One is the example.html, which is this one, and I also have another file, which is app.js. Let's quickly analyze the code. I have added the adapter.js file and the app.js file, and then I have a video tag ID for that which is local view. And on the app.js, I have created three functions. One is for gotStream, the other one is onStreamError, and the third one is setUpConnection. I have a variable called constraint, for which the property for audio and video port is true. Here, we are calling getUserMedia function. I'm passing the constraint onStreamError and gotStream. If it works properly, the browser will show a pop-up for asking user permission to access the camera and microphone. Once the user clicks on Allow, the success callback function will link the media stream to the video element of the HTML file. As we have our files ready, keeping our fingers crossed, let's run this. It isn't working. What went wrong? WebRTC functionalities were not thought for local files, but for online ones. Chrome doesn't permit WebRTC to work in cases like ours. We need to provide our files on a server, so we'll build an easy one. There are a lot of possibilities for doing this, but we won't introduce them now because we want to focus on WebRTC for the moment. We'll use the JavaScript utility Express, which will enable us to serve our file from our local IP, while the app is running and listening for requests. Node.js will run the application. I have the server ready. I'll just start. Let's go to the browser and open the application. The server is listening at port 8000. And voila! You already have the media, ready to be sent. Just click on Allow. That's what we've learned in this video. How to make our browser able to receive data from a camera or microphone, essentially by using just one function, which is getUserMedia. In the next video, we'll study the peer connection object and how an STP message is created and sent to make a negotiation between peers possible. Hello everyone. In the last video, we finally get our audio and video working inside a browser. In this video, we'll see that once we already have our stream, then we need another JavaScript element for giving it our media to be shared with other people. That element will be the peer connection object from the WebRTC API. Besides, depending on which browser you have, which version, or even on the specific constraints you want to set for your applications, for instance, if you want or not to allow video, audio, the other peer should know which capabilities can be expected from you, and which one of theirs has to be offered in consequence. Our first step will be to create a peer connection in JavaScript. This is quite easy. Following this example, code example followed https://webRTC-hyphen-experiment.com/docs/webRTC-peer-connection.html. You just need to specify the ICE servers and the optional arguments. We are creating a new object called connections. It accepts two arguments, which is the list ICE servers, which we need to specify, and optional arguments. We see here two different arguments. ICE stands for Interactive Connectivity Establishment. For the developer, it shouldn't be more than specifying the location of the ICE candidate. But internally, it tries to reach the destination through ICE via an internal process called ICE gathering. out of scope for this course. We'll introduce ICE and other possible servers in more detail in the next video. Optionally, we'll pass a flag for telling the connection to use DTLS, a security layer that protects our shared information on its way to the other person. On the other hand, SDP will be used to let the other browser know what media characteristics we are going to use in our media session. It's a very used protocol, mainly in VoIP, not only WebRTC, but summarizing, it is a piece of text which specifies a set of parameters previously to a media exchange session. The SDP generated by a peer connection must contain information about how to be reached by another one through a network, and also constraints related to media, codecs involved, and protocols. Let's quickly see how it's done in the following article written by our colleague Anton, The Anatomy of an SDP Message, webrtchacks.com/SDP-anatomy. First set of lines are referred to as global settings. Then, some audio specifying the protocol used for real time, specifying some codification parameters and information about the source from where the audio provides. We have a complete description of the audio media. Well, as the video is exactly the same, almost identical fields. Not so hard as it seems, does it? Two SDPs, an offer and an answer, have to be sent if we want to establish a media session between the browsers. That's what you currently see here. Let's explain the part of the process involving those SDPs. Peer connection provides the method createOffer for creating an SDP, and it's called as follows. The method needs two callbacks, one if the call is a success, and another one if it's a failure, and a third argument containing optional or mandatory constraints, for example, wanting or not to share video. Inside the success callback, you're expected to store your SDP using setLocalDescription and then to send it. CreateAnswer will be called in the other peer once the original SDP was received. Once again, two callbacks and some options. This time, answering means negotiating the media. Knowing the caller SDP, it's stored as a remote description and matched to the callee possibilities. The result, a new SDP containing the full match. The answer, including negotiation, which will behave as local description of the callee and will be sent to the original caller. In this video, we learned how to manage a connection between two people using WebRTC API. As you might have noticed, the negotiation process, that is, the exchange of SDP offer and answer, requires to be preceded by a lower level information exchange. We'll take care of all that in the last video of this section and in the signaling section. In the previous video, we dealt with the establishment of a connection from the point of view of the client code, not taking care of at all what's really happening in the middle of them. In this last video of section 2, we'll learn about some techniques used for dealing with the following issue. How can two peers exchange information for establishing a session before they know how to connect between them? We will be using turn and stun as tools for dealing with IP translation. We said that signaling and ICE candidates were different problems and that we have to deal with them both. Let's skip signaling and focus on the next step for now. As we already mentioned, WebRTC permits the peers to know their locations using an ICE approach, or Interactive Connectivity Establishment. It basically consists of selecting network candidates on each peer, with IP and ports, for being part of the SDP negotiation. For instance, my Wi-Fi card on my laptop. But you may anticipate the problem. I'm using a local IP provided by my home router. I can't be reachable for other people using this one, or even if I'm not at home. It could also happen that I'm unknowingly behind a proxy. Why not? ICE candidates are servers, reachable through DNS. The peers send a message to them and their origin IP can be taken. Those servers can work in different ways, and ICE tends to use the proper one for each situation. The most common ones for WebRTC are obtained from turn and stun servers. Both turn and stun are tools for dealing with IP translation when NAT routers or proxies appear in the way of our connection. Turn can deal with symmetric NAT using a proxy. A turn server is more complex, so the cost is higher and it isn't always desirable. For example, in terms of latency, it could be worse. A turn server could work well in almost any network scenario. Stun is faster and connects with peers without any proxy. It allows the browser to discover its public IPs so that the media can be sent directly. This is desirable in terms of cost and latency. But as I said, not always possible. Anyway, ICE will handle this complexity for you, and it always tries to find the best path for the media. You don't have to worry about that, but it's good to know about it. In conclusion, these ICE candidates will exchange the IPs of the two peers that want to have a connection between them. But under that statement, we arrive to another question. How do the peers know about the call intention and which ICE server is available for use? Do you now see the need for signaling? Somewhere, you'll want to have a meeting point for peers, a server who can reach all of them. If Alice tells this server that she wants to call Bob's number, this signaling server will have to notify Bob. Both users should have been registered previously on it. Once both agree on having a call, that's when the SDP exchange takes place, and also the ICE process. In this section, we explained the magic which makes possible the peer-to-peer connection between browsers to exchange real-time audio and video. ICE will work automatically. You just have to exchange the candidates along with the rest of the SDP. In the next section, we'll see how to let the other browser know that we want to establish a media session with it, and all the parameters of that media session by exchanging the SDPs. Hello and welcome to this new section, Section 3, where we'll be studying signaling, the last element we need for developing a full WebRTC application. Signaling will provide a point where the peers can meet. In this section, we are explaining why there is no signaling protocol for WebRTC, and the fact that forces the programmer to look for a signaling solution outside of the WebRTC API. We will also learn how to program a simple Node.js server. This is the first video of this section. In this video, we will understand the need for a signaling protocol. We will also go through the arguments needed for standardizing a signaling protocol. We will also debate between the pros and cons of signaling. As we have already said, WebRTC apps won't work unless the peers find a way to tell each other how they can be reached. And this is a step to take into account before the ICE exchange. Peers should register in a place where, if somebody wants to connect to them, a notification will be sent for starting a negotiation. Could WebRTC implement a signaling protocol? Yes, it could, but it didn't. Why? Because there are pros and cons related to this question. We are going to enumerate some of them. Let's talk about pros. Some experts say that a signaling protocol inside WebRTC would be an unacceptable constraint to it. Nowadays, there are different protocols for signaling messages without a standard one. The fact that WebRTC could fit with any of them makes it attractive. You don't need to adapt what already exists to WebRTC in principle. If you want to connect to a telephone line which supports SIP as a signaling protocol, you'll be able to use it with WebRTC. Summarizing, if you want to take profit of the advantages of another protocol to work with different ones, you will be able to. Let's talk about cons now. Designing your own signaling interface would not be easy. A connection has to be kept to be directional, and this breaks the original idea of HTTP of unidirectional service. Using WebSockets, HTTPS and other tools, you can solve those problems, but sometimes there's still a risk of having timeout disconnections if the network complexity is high. For this course, we'll focus on the simplest and fastest alternative. We won't try to consider as much context as possible. We just want to see a basic WebRTC app work and understand how it does so. In this video, we've learned that we have a new problem, the signaling one. Since WebRTC doesn't implement it, the pros overpower the cons, because it's better in terms of flexibility and avoiding some problems, like complexity due to HTTP not prepared to be bidirectional. In the next video, we'll learn about the three main solutions capable of providing signaling for WebRTC. Welcome back to section 3, where we're learning about signaling, which is the last piece in the WebRTC puzzle. In the previous video, we said that one of the possible pros of not implementing signaling is the ability to adapt different signaling protocols. In this video, we'll talk about 3 approaches available to WebRTC. All of them use WebSockets, creating a bidirectional link between clients, or clients' ICE candidates. They are SIP-OWS, SIP over WebSocket, XMPP-OWS, XMPP over WebSocket, and JSON OWS, JSON over WebSocket. Since any of them could be used in the industry, we want our app supporting as many as possible. Session Initiation Protocol, or SIP, is a signaling protocol oriented to the control of media sessions, mostly for VoIP. Used over WebSockets, we'll get support for our calls between distant peers. One thing we have to keep in mind is that SIP doesn't have security, and you might be interested on transmitting SIP over other protocols with encryption, as Secure Real-Time Transport Protocol, SRTP, or Transport Layer Security, TLS. Extensively, Messaging and Presence Protocol, or XMPP, is another alternative. It's based on XML, the markup language, and it was originally designed for instant messaging and presence. But finally, it was able to work for VoIP applications, file transfer, gaming, different uses typical from social networks. Finally, JSON, which means JavaScript Object Notation, working with WebSockets, is an attractive solution for WebRTC, since it shares the same syntax as WebRTC API. That means your app doesn't need to use other languages for taking care of signaling and media handling. We have briefly talked about 3 protocols capable of describing a media session that we need for WebRTC. Related to that fact, in the next video, we'll talk about the things we need from signaling that will make WebRTC work. Welcome back to section 3, where we are learning about signaling, which is the last piece of the WebRTC puzzle. In the previous video, we learnt about 3 different signaling products, which combined with WebSockets will provide proper signaling for WebRTC. In this video, we'll see what we need from a signaling protocol to get WebRTC working, which of these methods, events, and objects need a signaling server to offer users as much capabilities as possible. We will also look into the communication between an application and a server. From the point of view of the app should get almost full control of the server, at least according to the sessions handling. The app should tell the server which is its IP and whatever the server needs to identify it. From the point of view of the server, it needs to listen to peers' messages and save information related to them, and to the sessions established between them as well. This is where WebSocket is the best fit to transmit message quickly. We are going to use Socket.io to listen to peer messages and emit the messages. Socket.io has the on function to listen to the event, and once the event is triggered, corresponding callback will be called. In this case, if there is a message, corresponding anonymous callback will be called. Both the app and the server have to keep in touch. This will be possible through events, triggered each time the peer asks for something to the signaling server. Server will notify the other peer if needed, and it will save state information. So in our code, this is being achieved by simply using Socket.io. We catch the messages using on method and broadcast them to peers using emit method of Socket.io. Same at the client-side messages can be sent to signaling server using emit method. And when client receives a message from server-socket.on method, will be called, which will call corresponding callback function. So in this video, we have briefly introduced our needs from a signaling protocol. In the next video, we'll see how our example implements those necessities. Welcome back to section 3, where we are learning about signaling, which is the last piece of the WebRTC puzzle. In the previous video, we listed some of the needs from our signaling example. In this video, the last of this section, we'll be programming our own Node.js signaling server, implementing all the features previously mentioned. We will be looking at how to pass data between peers. We are following the example from CodeLab available at Bitbucket's WebRTC repository. I'll assume you have Node.js installed. If not, it's pretty simple. You can go to nodejs.org/en/download. For Windows, you have MSI and exe. For Linux, you have tarball, and for Mac OS, you have package. You can simply download and install it. If it's already installed, you have to run command npm install, and it will install dependencies. Let's understand the folder structure first. We have the package.json file and step folders. Package.json contains the dependencies for Node.js. When we run the command npm install, this file is being read, and all the dependencies mentioned in this file gets installed inside Node modules folder. In my case, I have already installed it. We will follow step 7 here. If we go inside step 7, we can see we have index.html, server.js, and folders to keep JavaScript, images, and CSS file. After that, with node server.js, Node.js will run a server in our computer, providing signaling. Let's see how. Taking a look inside the code. Let's open server.js first. So we are using the socket.io. The JavaScript library, socket.io, allows us to easily manage WebSockets. Clients, who are two peers, will connect to the signaling server. When that connection is notified, the server will start listening to messages from that client, not before. Look carefully at the indentation. Rooms can be created in the client, and the server will store them. If we check our code, we have the log function, which is for debugging purposes. Interestingly, it pushes the log messages to the client also. Socket.emit function is used for that purpose. Socket.on message will be called when clients send a message, and corresponding callback function will be called, which will emit messages to other clients. Now, let's check out the client-side code. We have the video tag for local video and remote video, and our index.html includes 3 JavaScript files: socket.io, adapter.js, and main.js. We already know the role of socket.io and adapter.js. Let's check out main.js. The JavaScript code is large, and we won't focus on it at this moment, since we are interested on signaling. But I want to call your attention over the following. The message event of socket.io. So whatever the message are being sent from the server, client will receive them here. So if the message is equal to got user media, maybe start, function will be called. Same way, if message type is offer and initiator and started is set, maybe start function will be called. So, depending on the message received from our signaling server, client will call function. Now, let's check out maybe start function. This function checks for 3 flags: is started, local stream, and is channel ready. And if condition passes the it calls create peer connection method, and streams gets added to local video. Create peer connection is the method where magic of signaling happens. This function create RTC peer connection object and calls handle ICE candidate. If RT connection is created, remote stream is added to the remote video. See, there are more lines that we aren't going to focus right now. Let's check out the demo. Let's start the server using Node server.js. Remember, our server is running at port number 2013. Let's go to browser and open the page. My local IP is 192.168.0.101. So I'm going to put it on my browser. So just enter the room name, and I'm going to use WebRTC test. Now I have another laptop also. I'm going to open the same URL from that laptop, and when it asks for the room, I'm going to use the same room name, WebRTC test. And yeah, here it is. Can you see the other angle of the chair, which is coming from the remote station? There are many logs written to console. You can go to console and check it for debugging and understanding purpose. In this video, we've learned how signaling works. I know there's a lot of code that you may not understand yet, but it isn't so complicated if you give it time. You've learned all the basic concepts of WebRTC, and we should be proud of ourselves. Now relax review what you've learnt, and if you have any doubts, just mail us if you want. We are ready to put together all the WebRTC pieces we have to create a full WebRTC application. That's what we'll be doing in the next section. In the next section, we'll become more familiar with the stream handling, which is part of the code we didn't explain yet. You're almost there. If you stay a few minutes more with us, you'll learn how to put all the pieces together. See you. Hi there, and welcome to section 4. Now it's time to move further. In this section, we'll initiate, receive, and establish our first WebRTC session. In this video, we are going to learn about HTML5 and JavaScript. In the end, we'll also see some parts of the code, where the media is asked for and the signaling room is created. In the previous section, we followed CodeLab example from Bitbucket's repository. It's the official WebRTC example from official Bitbucket repository. You can access repository from bitbucket.org/WebRTC/CodeLab. We are following step 7, in which we have code for video and audio exchange, signaling, and even data channels. Not explained during this introductory course, but they are another tool of WebRTC. We'll introduce data channels by the end of this section. We already checked that for having a web app working on Chrome, we need to server it. Local files have limitations. Node.js will help us to launch a very simple server. Besides, on this server, we want to establish a WebSocket between two peers, a channel where the signaling can take place. Socket.io is a great solution for that. Socket.io is a JavaScript library for real-time web applications. It enables real-time, bidirectional communication between web clients and server. It has two parts, a client-side library that runs in the browser, and a server-side library for Node.js. Let's understand server.js code and Socket.io methods. If we open server.js in our code editor, we can conclude that it's not a long code, but it's quite powerful. It's helping us to run a web server. Just calling the HTTP library method createServer. After that, if we visit on our browser our local IP, followed by this port, which is 2013, it will be reachable. That we already saw. If we go to browser and type HTTP your IP :2013, we can access our server. By the other hand, let's see what's going on with Socket.io. So we created the app object, passed it to our Socket.io, and created a new object called IO. Basically, the IO variable listens to events for a certain server, our app. On each socket, some events have to be handled through callbacks, like in this case. If there is a message, this anonymous callback function is going to be called. In the same way, if there is an event called join, this anonymous function is going to be called. Log function. It's just for the debugging, logging the arguments of the connection, and it also sends the log back to the client side, which means in our browser. Message callback. It's used for when we receive a message from one peer, we'll send it to the other peer. This sounds like signaling, doesn't it? Finally, with the create or join event, we'll create the room if it doesn't have any participants, or we'll join if there's another peer. Notice that all these bindings are established once the socket got connected, and not before that, as expected. Let's see now the main JavaScript code, containing the truly WebRTC code. This code is served from JavaScript file, which is inside JS folder file called main.js. First, we have some constraints for the WebRTC server. We have the constraints for ICE servers, we have the PC constraints, and we also have the constraints for SDP. We want our peer connection to use data channels for chat, to use DTLS, and we want our SDP to force audio and video. That's why we have mentioned offer to receive audio and offer to receive video both as true. Then we see that here the socket object is created. We create, or join, our room by sending an event through the socket. The answer will be listened as well with these events. I think it wasn't so difficult, and socket.io lines are actually recreating our signaling server. So if there's a message called created, this callback function will get executed. If there is a message called full, this callback will get executed. If we take a look on how we get our media, we can observe that two callbacks are sent: handle user media for success and handle user media error. The first one is the success callback, and the second one is the error callback. If success, handle user media function will be called, and will attach the media stream to our local video stream. Besides, at this point, maybe start will be called if the current peer is the room creator, but the call won't be done until two peers are inside, which is indicated by the variable isChannelReady, set to true when the other peer joins. Maybe start will be called again once we know that the other peer has reached its user media. Then, the peer connection is created by calling the function createPeerConnection, and the negotiation begins. But we have that part for the next video. Please be patient. The end is near, and you're almost at your goal. In this video, we introduced the example that we are going to follow, the two JavaScript tools in which it's based, and we examined the code parts related to signaling and to get the user media. In the next video, we'll dive into the ICE candidates, exchange, and the SDP negotiation, studying the rest of the code needed for running this example. Welcome back. In the last video, we saw how to set a few callbacks for providing signaling using socket.io, and how to get the user media according to our constraints. In this video, we plan to teach you how to receive a WebRTC session, how a SDP is offered and answered, so the peers can be connected. This includes the process of ICE candidates exchange. Let's go back to the code where we were before. We said that if both peers are ready, the initiator will call the other peer. But first, a peer connection has to be created according to the constraints set by PC constraints. Remember that PC-config contains ICE candidates. Then, doCall can be executed. So this function will basically check the browser and merge the stream and call createOffer function. For sure that you remember it. Set local and send message is the success callback. It basically puts the obtained SDP as a local description of the peer connection and sends a socket message with the SDP. The SDP is offer type. That's very important because that message will be filtered by its type. When an offer is received, the receptor sets the SDP as the remote description, not the local one, and creates an answer. During this process, events related to the ICE candidates will be triggered directly by the peer connection object. We've replaced the callback on ICE candidate from the PC object by our method handleIceCandidate. The object sends through the socket the obtained candidates, after reading them from the local SDP. When receiving that message, the ICE candidate is added to the peer connection of the other side, creating a link between those two peers. We arrived at the end of this video. We've seen the rest of the elements needed for establishing a WebRTC video call, which were the SDPs and the ICE candidates. In the next video, we'll run the example to see that it currently works, and we'll talk about what would be needed to set our app online, and we'll finally introduce the data channel use by this example. Hello again. This is the last video of section 4. We've already visited all the main lines of our example where WebRTC happens. In this video, we'll see the example working, and then we'll discuss briefly what we need for putting our app online. And finally, we'll introduce data channels. To run the application, all we need to do is go to the directory. So if you are running the application for the first time, all you need to do is hit the command npm install. If you have Node.js installed. I already installed the dependencies, so I won't run this command again. Then we need to go inside Step 7 folder. Once you are here, all you need to do is to run node server.js and hit enter. You see our socket.io server is getting started. and it's already started. All you need to do is go to the browser and type your local IP address with the port number. Remember, our Socket.io server is running at port 2013. Once you enter, it will ask for the room name. I will use WebRTC test once again. Once you hit enter, it will ask for the permission for your webcam. You need to click and allow. And yes, I can see my local stream. I have another laptop set up. All I need to do now is hit the same URL there, and when it asks for the room name, I will use the same name, which is WebRTC test. If everything works fine, I should be seeing the remote stream at this screen. Let me hit enter, and yeah, here it is. Can you see the other angle of the chair? It's working perfectly fine. When we analysed the code of the server, we saw that we had a log function, so all the logging is done from there. But you may think that this example is not fair, since it's not a public server, but a local and private one. That's right. For that, you would need to register a public domain, but it will work exactly like this, just changing the IP. Or using a virtual private network, VPN, for simulate that the peers are in the same network. In this case, if your server is public but your service isn't, you may think to use credentials, to ask the peers to log in, to identify themselves before being able to call. Finally, let's introduce data channels. We saw in the application a simple chat made by using data channel, another feature of WebRTC that we haven't covered yet. Basically, it consists on taking advantage of the peer connection established and creating a message-oriented channel. Reliability and delivery order are configurable, and we also have an API for that. So if we go back to our function, create peer connection, and if isInitiator is set to true, while sending the channel, we are using the API function called createDataChannel, where we are passing the sendDataChannel and reliable is equal to false. Like we said, we can set the reliability while sending the data channel, and when there is a message, handleMessage function will be called. This is how you create sendDataChannel. When isInitiator is equal to false, at that time we call the receive channel, where the receive data channel is being called. And if there is a message, handleMessage is called when data channel starts. HandleReceivedStateChange is called, and on close, the receive data channel. HandleReceiveStateChange is called again. So basically, data channel helps us to send and receive messages. In this video, we've seen our app working, which is wonderful, and I hope you understood all the steps. Ask us if you don't. We are here for you. Besides, we've also learnt some hints for putting our app online, and some details about data channels. In the next section, we'll debug our own app by using a lot of developer tools that Google gives us, developers. That's all for now. Thanks for watching. Hi there, and welcome to the last, but not least, Section 5. In this section, you'll discover the tools which will help you to debug and improve it. We will look at how Java Console works in a browser. We will also peek into WebRTC internals. As you should already know, WebRTC is a technology for browsers, so you will find in this browser almost all the debugging tools you need. In the first video, we are going to see the browser console. This is not a specific tool for WebRTC, but it provides detailed information about the load process, files, delays, and the JS which is executing in the page, so this tool will be a great help. Then we'll dive into the WebRTC internal page, which gives all the information you need about the WebRTC sessions, which are established in the browser. This page will be really useful to find out why your WebRTC is not working as expected. Finally, we're going to check both tools during a video conference using our app. Both Mozilla Firefox and Google Chrome offer a very helpful console. You can open it by just right-clicking on any element of the web page. Right-click and inspect element. Or going to the Chrome menu and selection with the More Tools option and JavaScript console. The way to access the tool in Firefox is almost the same. You can click on the right button and select Inspect Element. Or you can go to the menu and select any of the first server options in the Developer menu. When developing WebRTC applications, the most relevant will be the JavaScript console, where the browser will show all the JavaScript errors which may happen during the use of the WebRTC API. It is useful to add console messages in your code to be able to detect when the error happens. On the other side, there are some stats given by the WebRTC API, and Chrome and Firefox take an advantage on that fact, parsing them and putting them entirely at your disposition to check what's going on with your streams. For instance, I'm going to set up a log when user is being asked to access camera or microphone's permission. Let's do it. OK, let me open my app.js file. So I'm going to put log as soon as the success callback of got_stream is being called. Let's call this success callback is being called. I will just save the file. Let's go to Chrome and check it out. You can right-click, go to Inspect Element, go to Console, and as soon as I say Allow, there it is. Besides string, we can also log variables. Besides, we can visit WebRTC Internals tab. We can go to Chrome://WebRTC Internals. Here we can see much information like the caller origin and the process ID. If the streams are being passed, you will see more information about the peer connection. You will see graphs, statistics, and lots of things. In this video, we've learnt about the two main tools provided by the browsers that we want to make the life of the WebRTC developers easier. In the next video, we'll focus on the consoles, surfing the different functionalities they provide, as events listening, dynamic code, or HTML code access. Hello again. In the last video, we introduced the main debugging tools that we're going to learn about in this section. In this video, we'll see how to use the developer tools for both Chrome and Firefox, which are versatile consoles capable of looking at app logs, surfing the HTML, CSS, JavaScript code, monitoring events, and so on. We'll focus on Chrome, but they're both pretty similar. You can right-click on anywhere on the page, click on the Inspect element, and open the Chrome's developer tool. Alternatively, you can also press Ctrl-Shift-J. By default, the first tab will get highlighted. Let's check out the console. All the messages will get logged in console. If we hit the filter button, we are able to see type of messages. We can see the network messages, errors, warnings, info, logs, and debugs. We can also filter by typing here. Let's say if I type room, we can see all the messages which has room inside text. There are different kinds of messages, such as errors, logs, warnings, and all of them can be sent by JavaScript methods. For instance, console.log will print in the console the string or variable we want as a log message. Imagine that at one point of the execution, something is not working as expected, and you have no errors specifying what exactly happened. If you know the code, the variables or methods involved in your functionality, print them. Maybe the variable doesn't have the expected value, or maybe you aren't calling the method at all. Let's check out the Audit tab. If you click on the Audit tab, you can run a fast evaluation of your app, done by Chrome, suggesting you improvements related to the network utilization and to the web page by itself. In the first case used, they tell you how to organize your served files to improve the load, and in the second one, for instance, some simplifications you can do in your CSS style code. All you need to do is hit Run. Once you hit Run, it will suggest the improvements which you can do in your application. Like it is giving us two suggestions: enable gzip compression. If you click on the arrow, you can see we can use the gzip compression on these files, which reduce the size of the files and network utilization can be improved. Similarly, it's also suggesting us to use browser cache for all these files, which will help us improve the application's overall performance. Let's check out the Resources tab. Let's suppose your application is using WebSQL, indexed DB, local storage, session storage, cookies, application cache, or cache storage. All these things you will be able to see it here. Suppose your application is using cookies. All you need to do is go to Cookies, and you will see the cookies value here. Same with the local storage. HTML5 has the functionality of local storage. If your application is using local storage, you will see key and value here. Pretty handy. In the Profile tab, we have two different profilers, which will help you locate where you waste most of your resources when your code isn't optimal. We're talking about CPU time and also memory leaks. The CPU profiler focuses on JavaScript functions. The heap profiler studies the memory distribution, its use by JavaScript objects and DOM elements. The snapshot can be at a certain instance, or you can run the profiler for a while to see the evolution of the memory when you interact with the page. Let's check out the CPU profile, and let's hit Start. You see the profile is starting and reading. All you need to do is play the web page. Once done, you can hit Stop button, and you can see where your CPU time is getting utilized. By default, it's sorted using heavy, bottom up. You see the time is in millisecond total time taken. You have different view options. You can use the tree option, or you can use chart to visualize the same. The Timeline tab offers a better report of what's happening among the time by listening to events, contents load, and so on. So, if we reload our application, you can see it's giving us a very nice picture about what is happening, the response received, when it finished loading, when the HTML parsing got completed. All this can be seen here. So, we are capturing the JavaScript profile. You can also capture the memory, similar to Profile tab. Again, you have the option to filter out most of the things. On the basis of loading, scripting, rendering, and painting. You can also see resources which have taken time more than 15 milliseconds. If you run the application on the server, this can be pretty handy. Sources tab. It's similar to Resources tab. This sounds funny. In this case, we don't have information about stored data, but we have listed other scripts that may affect our application. For instance, the used by determined extensions, like advertisement block ones, and etc. So, in our application, we have the JavaScript, which we are using main.js, adapter.js, and in our application, we are also using socket.io.js. So all the resources we are using in our page we can actually see here. You don't need to go to your server and check. The good thing is you can also put the breakpoint. This is pretty handy. Let's say if I put a breakpoint here, all you have to do is click here and let's reload our application here. So I have a breakpoint at this line. Once I move forward, it's asking for the room. Let's put the room name, test, and you see it. I put a breakpoint here and it stopped here. So breakpoint can be pretty handy. Once I move my mouse here, you can see much information about the objects. So this is pretty handy for debugging purposes. Finally, network and elements. The Network tab allows us to visualize all the traffic which is exchanged between the browser and different servers. In a WebRTC web application, this traffic will normally sent and received from the web server, which is hosting the page. And if we are connecting WebRTC with a different technology, e.g. a VoIP SIP network, the signaling traffic exchanged with the signaling element of the gateway, which translates the signaling and the media from the WebRTC to another different thing. So, I reload my application and go to the Network tab. I can see Socket.io is getting loaded, Adapter.js getting loaded, and also Main.js. If you are using WebSocket for signaling, you can check the frames which are being sent by clicking on the WebSocket URL and then on the Frame tab. It may not be easy to read, so we can see that we have WebSocket URL here. Click on it, and we can go to Frame and check out the frames which are getting passed. The Elements tab is the last useful tool that we'll learn here. You're allowed to select the different DOM elements, being highlighted when you put the mouse over it. And you can change the style rules while running the app to check different styles without reloading the page. They won't be stored, so feel free to experiment all you need. Let's select this text area, and if you want, to put a border. I can go to Style and Right Border 2 pixels red solid. Do you see? I can also increase the height, let's say 400 pixels for that particular div. I can change the background color to, let's say, blue. So you can experiment with the styles and event listeners using the Elements tab of the developer's tools. So, in this video, we've seen one by one all the different tabs we have in the developer tools. I bet you can imagine the advantages you can take when you get used to them. Firefox dev tools are quite similar. Once you've understood the Chrome tools, you'll be able to understand the Firefox tools. In the next video, sadly the last we stay together, we'll see how Chrome WebCRT internals and Firefox about::WebCRT work. The Internals tab, where we can follow the SDP negotiation and looking into different streams of peer connections. Hello and welcome to this last video. For the moment, the end is near, and we hope that you leave this course with a clear picture of the basics of a WebRTC application. In the previous video, we went deep into the consoles, exploring the different functionalities and accessing the code and the elements. In this video, we're going to visit the browser tabs where the WebRTC stats are displayed. That's going to be useful, since we can determine if a media content is being transmitted or not, for instance. As we mentioned in the previous section, Chrome://WebRTC dash gives the developer all the information related to the WebRTC sessions and media capturing, which is happening in the web applications being executed by the browser. In Mozilla Firefox, you have quite an immature equivalent of WebRTC internals. You just need to type about::WebRTC in the URL bar and you'll get access to it. The first thing you'll see when you open WebRTC internals is the list with the peer connection objects which have been created by the JavaScript code executed by the browser. Please note that you can have several peer connection objects running simultaneously, so you have to check the name of the URL. Once you choose a peer connection, an event list is shown, with all the events launched during the SDP negotiation and ICE exchange. You can even take a look into the created SDPs. If any of those processes are interrupted, you can check it here. Besides, below that list, Chrome offers us real-time stats related to our streams. The variables starting by SSRC are referred to the streams, local and remote, in this case, sent and received. How can we differentiate between audio and video? That's easy. Take a look, for example, at the graphs displaying the evolution of SSRC variables, when they're talking about frames and different video information. You have video, and if not, if it's referred to audio level, echo cancellation, and so on, it's audio. If one of them doesn't work, you can study here why that's happened, and if there's at least a stream created or not. On the other hand, Firefox offers a similar tab as well. Firstly, we find the ICE candidates list for audio and video, and the ones selected. Then, the SDPs, local and remote. Then, there is once again a real-time stats parsing. But this time, there's no update in real-time nor graphs. So we have to refresh the page in order to obtain new levels. We hope that Firefox will improve on it. Finally, the capability of recording logs of the connection. In this video, we've introduced the basics of Chrome's WebRTC internals and Firefox's About WebRTC. This is the last video of this introductory course to WebRTC applications. We hope that you've liked it and that you've learnt enough to start developing your own apps easily. It's been a pleasure. Thank you for your time. Write to us if you have any doubts or suggestions. Goodbye.